This recording deals with the 7 base units used for measurement, deriving new units, and then converting between these units. And we're going to start with just simply defining the 7 base units. Length, our first unit, is just simply the distance between 2 points. Now, the unit for this is meters, M-E-T-E-R-S. Sometimes in IB physics you'll see it written as M-E-T-R-E-S, which is a little bit more European in terms of how it's used. And the simple abbreviation for this is just M. We in America a lot of times we use feet, but we want to get used to SI units or international units, which is then going to be the meters. Mass, the amount of matter in an object, is given in kilograms, which has an abbreviated unit of kg. Time, the interval between two events. It might be the starting and stopping of a stopwatch, the beginning of a day, the ending of a day, something like that. The bell rings to start the class period, it ends the class period with another ringing. The interval between that is what we call time, and that is measured in seconds, S-E-C-O-N-D-S, with the abbreviation is S. Electric current is basically how long a certain amount of energy, how long it takes for a certain amount of energy to flow from one point to point. What we do that is what we measure that is in amperes, or a big capital A. Now that will become a lot more familiar. We'll become more familiar with this later on. Temperature. There's 3 different temperature scales you're probably somewhat familiar with. Fahrenheit here we know a lot about. Celsius we know some stuff about, but the one that we want to know about for this class is what we call the Kelvin, or simply abbreviated with a K, based on absolute zero, the lowest possible temperature that we can ever have. The amount of matter, if you remember back to the chemistry days, if you've had any of that, know that there's something called a mole, which kind of refers to how many atoms there is. It's abbreviated MOL, which means you just lost an E. And then finally, light intensity is measured in something called a candela, or a CD, which basically is how bright some light is. We'll get into these more when we go through the different parts of physics with these things, but that's just giving you some basic base units of what these things are. When we do calculations with these things, these units then get combined and they become bigger, more complex units. We're going to start with a very famous formula developed by a very famous scientist named Isaac Newton. This is one of his very famous laws, F equals ma. What this basically stands for is force equals mass times acceleration. Now, we've only talked about mass in our fundamental ones. Our force and our acceleration are different units. But what I can tell you in terms of units is force is going to be measured in something called newtons. Well, we don't really know what a newton is. And one thing you want to become very good at in physics is being able to break complex units into their base and their fundamental units. It'll help you a lot more when it comes to understanding where these things come from, or even how to derive your own formula to come up with a new unit, or to come up with a base unit that you're looking for. Remember before, hopefully, that mass is measured in kilograms. But acceleration is measured in something called meters per second squared. So what we're seeing now is a newton is basically equal to a kilogram times meter per second squared. Now IB likes their notation like this: kilograms times meters times second to the -2. Basically this and this are the exact same thing. But this is just a different way of noting it, and if you don't do this on your final test, you're going to have some marks taken off, and you'll find out what those are in a little bit too. These are what we call derived units. A derived unit is a combination of 2 or more SI units. So it can be something as simple as 1 divided by a second. That's equal to what we call a hertz when we talk about frequency. This is really just a math operation. It has the same SI unit as time, but now we're doing 1 divided by time. So it becomes a little bit more complex, and that's why they give it a new name called a hertz. And we'll talk about those in terms of frequency and stuff like that later on. So the next thing you want to do is do some very simple conversions. I'm actually going to go back to the following slide. I'm going to clear that out. And we're going to walk you through what I call factor label method. And what that does is kind of makes it easy for us to cancel units and understand what they're being converted into. For example, I'm just going to give you something like 40, oops, I need to select a pen. I'll go with this color red here. 42 meters equals how many, question mark, centimeters. So to do this, what I would do, some people understand how to slide the decimal place, and if you have the prefixes memorized and stuff like that, that's okay. But for our purposes, we're just going to start with very simple conversions and just say, okay, I'm going to go 42 meters. Now I want to multiply this by something that's going to change this appropriately so we know how many centimeters are in a meter. And what I have to do is put my units in the proper spot. So just over here, I know that every meter, 1 meter, has 100 centimeters. Now I can look this up on my physics data sheet or on my conversion sheet, but I have to take these two numbers and now put them in the appropriate spot. And this is like multiplying something by 1. You know, if we had like 8 times 1, that's always going to equal 8, or 1.21 times 1 is always going to equal the same number times that whatever. This idea of multiplying by 1 is how this factor label method came about. So we have to put things that are equal, one above and one below. And then if you remember fractions, if you have the same number above and below a fraction bar, they cancel off, and what you're left with is 1. So what I need to do is put meters in the right place so it cancels off. And in this case, it's below. You can think of this 42 meters as 42 over 1 if it helps. And then I'm going to put 100 centimeters up here. I cancel meters off. I cross them off, put an X through it, whatever you want. And that means now I'm left with just centimeters. Now to finish this, I'm going to have to say, okay, that's going to be the same thing as 42 times 100 divided by 1 times 1. In this step I will probably not even put anymore after this, because it's so easy to just kind of recognize that 1 times 1 is 1, and divide anything by 1 is just the same number. When I do this, I end up at 4,200 centimeters. Okay, again, pretty easy, but what it does is it lets us see kind of how to use this thing called the factor label method and get very comfortable with that. What we want to do next is go to something where it's not as obvious what we have here. And when we get into things like power and energy, this will become a little easier for us, but sometimes you'll have questions about how many joules of energy are used by a 40-watt motor. Well, what a lot of people want to do is go get the formula, find out how to do this. And in reality, we can just use the unit of watt to kind of understand this. Now, I understand we're not familiar with watts yet, but what 40 watts is equal to is really the same as 40 joules per second. This makes it very simple. Understanding that relationship basically just says, okay, if I'm using this for 1 second, then I will have 40 joules. If I use this for 2 seconds, I use 80 joules of energy with my motor, and so on. So this is just another example of how we can very simply use our units to get an answer instead of having to go back and do a formula or a big conversion. Some other conversions we're going to work through are area conversions, for one. Now, area can be a little bit confusing because people want to go back to what they do with just regular length, and they want to move their decimal one place or another. For example, we'll start with, go back to this 40 number. We're going to go 40 square centimeters is equal to how many square meters? Okay. What a lot of people do is they're going to move their decimal 2 places to the left, and they're going to get 0.4 square meters. Wrong. Because this is a area conversion. Area, remember, is equal to the length times the width. So this becomes a much more complex conversion than just a simple length, because it's got 2 dimensions involved. So what I like to use my factor label method, and I might have to separate this centimeter squared. I'm going to do that right now. I'm going to say 40 centimeters times a centimeter. What that tells me is I got to do this twice. I can't just do it once. because if I do it one time, I only convert one of the centimeters. So I'm going to fall back. I hopefully remember that 100 centimeters is equal to 1 meter. Very similar to what we did before. We had our 42 conversion from a prior slide. But now what I have to do is convert and cancel. I got to know, where do I put this 100 centimeters? Well, I hopefully recognize I'm going to put this on the bottom and 1 meter on top. So I can cancel. In order to cancel, I have to have a number above and below. That one canceled off, and that one canceled off. Now what this would give me is centimeters times meters. That's not my conversion. I want to get that into something else. So I need to do the same conversion again, where I put 1 meter on top and 100 centimeters in the bottom. Now I can cancel off my other centimeters, and I end up with meters times meters. So to finish this, I'm going to, okay, I have 40 times 1 times 1 divided by 100 times 100, which really is going to be 40 divided by 100 times 100, or 0.004 square meters. I have the right number of significant figures. I don't have to change that. We had one here, so we can have one in our final answer there. So that is another way that this converting idea, that we can convert each of these, not just one of those, to get our final answer. And the last thing is a speed conversion. Let me cancel this out of here. We're going to cancel between we're going to convert from one speed to another. So I'm going to start off with a speed of, select a pen here. Let's go with this green one. Let's say, all right, I have 12 meters per second. I want to know how many kilometers per hour that is. Now again, I have two different things I have to convert. I have a length and a time, and you can see both of those got converted. So again, if I can expand this as long as I need to. So I go 12 meters per second. I'm going to multiply that by my first unit. Now I hopefully know that there are 1,000 meters in a kilometer, and I have to put my 1,000 meters on the bottom of this fraction bar again. So that and that both cancel off, and I have 1 kilometer left. Now that's a good thing. I have kilometers per second now. And what I need to do is convert this one. Now, I might know how many seconds are an hour. I might not. It doesn't matter. I can just simply go with what I know. I know for sure there are 60 seconds equals 1 minute. So I have to take these two numbers and plot, and put those into this. Now, this is below the fraction bar. The meters is above, so we had to put this meters below. But this seconds is below, so I'm going to put 60 seconds up here, and that's 1 minute. That means this cancels off with this. I have one above, one below the line, so they cancel off. Now I have this into kilometers per minute, and I just have to simply say, okay, what about minute and hours? What's the relationship there? Well, again, there are 60 minutes in 1 hour. And again, those two will cancel off, and I end up with hours and kilometers. So now I'm in the kilometers per hour. So to continue my calculation, I'm going to have 12 times 60 times 60 divided by, and again that's in kilometers, divided by 1,000 times 1 times 1, which again I don't need to write out the 1 times 1, but I did here, to get my final answer of 43.2 kilometers per hour, which when I know my significant figures I can only have 2, so now I'm going to put 43 kilometers per hour. And in IB, they like our notation different. They don't want this fraction bar, so they're going to say 43 kilometers times hour to the negative 1. Well, that's our video on how to convert and how to come up with derived units.